Okay, so today we're going to do the camera code, or not the camera code. I mean, we're getting there. We're kind of like adding bits and pieces of it, but before we do that, we want to make sure we have like a nice data set to test with. So we'll make a function for creating a default tile set, and then we'll wire it to a hotkey, right? So it needs to be some type of key we're not going to press too much, particularly something on the right hand. So I think P for pattern would be good. So P for pattern, right? Because it's on my right. It's the right hand on a QWERTY keyboard, and the right hand I usually want to be using the mouse, and the left hand I want to be using the hotkeys. So if it's a hotkey on the right hand, that means that it's a hotkey I don't want to be used too much. So once we figure out how to make that default pattern, we're going to also make a save utility, probably like right after pixname and pixback, or maybe after pixname, I think. We'll do a save utility. So like right here, we'll say, you know, to do and pixsave, right? And pixsave will be for saving to disk, and it'll use the file boy over here to achieve that goal. So, oh hey, so I expect in about, I'm expecting by this Monday to have something visual. I mean, it could be more time than that, but I'm getting pretty close. Right now, I'm just getting data to save to a PNG file, and that PNG file, whatever it looks like, kind of represents what's in my texture memory. And from there, I'm going to keep on writing the shader code. But yeah, so, and also, let's see, over here, I have a little chat thing somewhere. Hold on. Chat box. Let me throw this up here. So, unfortunately, I'm not very good at chat, so I have to, like, add some spaces. Oh, there you go. Oh, yeah, so, let me find a little demo file for you for a second. So, so if we go to the demos, and there is an old Golang, project I wrote, and it's going to achieve this purpose. Hold on, let me find it down here. So when I say 5D, I don't mean like something more than 3D in the traditional sense. I just literally mean, 5 dimensions, right? So where are you? You should be somewhere here. Okay, this guy right here. So let's see if we can go to YouTube here. Can I just hit the YouTube button? Yeah, so let me close this. So it's going to be something like this, where the 5 dimensions are, you have an X and a Y, right? So you have 2 dimensions for X and Y. Then you have a layer, that's another dimension. And then you have a tile exponent size. And then the final dimension is the tile value, or you could say the color, or the material that the tile is made out of. So we have these 16 cells here, right? And each one of these 16 cells, you could say we can draw with different pixel sizes. And if you're familiar with auto tiling, this is a little editor for creating auto tiles here. Can we actually full screen this? So I coded this a few years ago in Golang, and we're going to do something simpler, or similar and simpler. So for an auto tile set having 16 tiles, this is actually a lot of work for the artist. So we're going to make an auto tile set that is only 4 tiles. Oh, there's me zooming in. We're going to make an auto tile set that's only 4 tiles, and it's going to be the 4 corners. So it's going to be like top left, top right, bottom left, bottom right. And from those 4 tiles, we are going to hold on. From those 4 tiles, we're going to auto-generate a 16-tile auto-tile set. So if you've ever done auto-tiles, you're probably familiar with how a lot of the time you're doing a lot of redundant work, right? Like, auto-tiles can be so redundant that people have created like little helper applications to help artists make auto-tile sets by, inputting some source graphics and then, processing them and then creating the final graphics. So rather than making a tool like that, we're actually going to build in that functionality into the engine. The reason for that is if you have some type of auto-generating script where you're going to take a few source graphics and make more graphics, what you're really doing is you're wasting memory. Because you're doing something that can be auto-generated and saving the result as a whole bunch of pixels. So I would like not to do that. I would actually like to auto-generate those tiles on the fly so that the game data can be very, very compact. So this initial prototype uses like a quad tree-like structure to store this data. However, the current iteration, the current engine that I'm working on, stores all of this data in a quad tree that's stored inside of a texture. And that makes it really easy. It's also a 512 by 512 texture, and that enables me to really easily do memory dumps, right? Like if I want to know what's in that texture, what's in this quad tree, right, I can take the quad tree texture and I can just dump it to disk. And that also makes it really good for writing a GLSL rendering algorithm with it, right? We can't really get some type of heap allocated data structure into a GLSL shader. We really need it as a nice big solid chunk of memory, right, to get it to work in GLSL. So this project, though the final result is very similar to what I'm working towards, it internally is not, right? So a lot of times when you're trying to make a prototype, you can get to where you want to be visually very quickly, but to do it over again and get an actual solid foundation is like, I don't know, like from what I've been doing, it seems like almost 2 orders of magnitude more work. But yeah, so that's the idea. PAINT5D is X, Y, tile size, tile layer, and tile value. So those are the 5 dimensions. So 1, tile X, 2, tile Y, 3. And all the tiles are double the size of all the other tiles, right? It's an exponential relationship. Yeah, exactly, the redundancy. Yeah, exactly. Yeah. So yeah, we're gonna try to fix that by making this system. And I've already everything that I am coding right now. I've already done it all before. It's just that we're trying to coherently smash it all together, right? We're trying to take all those prototypes that I wrote in my demos page, and can we just exit this? Yeah, we're trying to take all the prototypes that I wrote in my demos page and make a coherent system. So right now we need some type of default fill pattern that we need to draw a default fill pattern to the texture we're going to render that has this very specific data structure, and then we want to output it to a bitmap so that we can just output it to a PNG file bitmap, and that way if we save the data as a bitmap, we can open up in an editor like a MS Paint or something and visually inspect it and make sure that the structure within that bitmap looks correct. And if that structure within that bitmap looks correct, then we'll be ready to start writing more of the renderer code. So the first thing we're going to do is a default fill pattern function. Then we're going to do this pixel saver, right? We're going to make a pixel saver sublibrary so that we can export our GPU data to a PNG file so we can inspect it, and then after that we're going to start writing more shader code. So I don't know if I have really much more to explain than that. I guess I could keep on explaining as I go, but it'll be kind of boring, I guess. I think hopefully things will gain up momentum as I get like more things visually on screen. First thing we need to do is just look for the unit test section in this code and put the new code just directly above the unit test section, right? So we have this unit test section. Everything beneath here is unit test. So you'll see that we're at about line 3000. And if you look at my little tab over here, my little scroll wheel, the unit tests are more than half of this code, which really is, it's a good thing and a bad thing, right? It kind of sucks that I'm spending all my time writing this code, but it's a good thing that I have a solid foundation. So we're going to go right in here, and we're going to say, like, default tile design. That's not how you spell design. Design. No, yeah? I don't know. So we're going to make a section for default tile design fill pattern. And with my sections in my code, they're not necessarily named verbatim after the function that's going to be in here. Like, maybe more than one function is going to be in this section. But we just want a nice little commentary where we know where the comment begins and where the comment ends. So I kind of use this style, right? We know the comment begins here because this is left justified. We know the comment ends here because this is right justified. So I think this should be, should it be private? Should it be public? I don't know. If we don't know if it should be private or public, we should just start off with something that is private. So we're going to do void, and we're going to do AAC 2020 PAINT5D, and default tile design fill pattern. That's to... We're just going to call it default design, or actually... we'll call it draw default design, or draw default. Yeah, draw default, or... I don't know what I want to call this. We'll call it draw default offset. We'll assume that there may be more than one, so we'll give it like a 1 overload, right? So obviously this is C code, so there's no such thing as overloads. So at the end, I'll put something that kind of qualifies as an overload by convention. And this will be void. We're going to hard code what it actually affects. So it's going to affect one specific piece of memory, and we don't really want to be using this on any other chunks of memory. Now, we can always refactor that later, but we want to be as rigid as possible when we're writing this code. So we want to avoid flexibility and just be very rigid about what we're doing so that the code is just easier to comprehend. So we got this default offset command, and now we got to figure out how to make like some type of default design. So let's open up Paint for a second, paint.net, and show you like what kind of pattern I think I'm going to draw. So I think what we're going to do is, where's my tools here? So I think what we're going to do is we're just going to do something like this. We're just going to try to put tiles all the way around one of the auto tile subtiles. And then we're going to do it for every single tile size, right? So for your smallest grain tile, we'll do something like this. And then for our larger next size up tile, right, we'll do something like this. We'll kind of surround the area with, you know, tiles of the next size, right? And then, and this is all going to be on the same layer. So these patterns are going to be overlapped over each other, and they're all going to be these different tile sizes. So we're going to do this, and then we'll go to the next tile size, and we'll do the exact same thing. So the next tile size is for the previous. So then we'll overlay something like this, where we have these next bigger tiles, but they'll just go they'll just surround the canvas, right? So we're not going to try to build any type of very fancy pattern, because this pattern is also going to be for debugging, right? So we need to be able to visually confirm that the structure is correct. So we're going to do something like this, and we already have all of the utility functions to properly manipulate the data structure. So let's not save that, and let's look at our PAINT5D notes file. So we have a notes file where we kind of kept all the signatures of all the functions so we can kind of reference these. So let's see, coordinate conversion, and here's the main interface for kind of drawing on here. Remember, I said there's 5 dimensions. So the 5 dimensions here are the tile exponent layer, the X and Y location, and then also this tile value. Now we have these other parameters here that are not part of the 5 dimensions, and these are for, this is for what subtile you are drawing on, which doesn't count as another dimension, and this one here is actually for what graphic you're working on, right? So this system is going to store up to 16 tile sets that you can create. And if we look at the memory for this, so let's go up here. So when we're talking about the tile quad, the tilqua, it's either this graphic, this graphic, this graphic, or this graphic. And we're looking at the actual data partition for those individual graphics, which corresponds to this part of the diagram, right? So the top left graphic, the top right graphic, the bottom left graphic, and the bottom right graphic. So as far as the Auset index in my notes here, so you see that there's this Auset index right here. Auset standing for auto tile set. So this Auset index, if we look at the diagrams, oh, wrong thing. If we look at the diagrams, that comes from bit packing, right? So we're going to take all 32 bits of a pixel, or all 32 bits of a pixel. Where's our 32? Oh, this is here. So 0 to 31, right? We're going to take all these bits of a pixel, and every 2 bits of the pixel is going to encode one auto tile set. So what that means is that each auto tile set uses 2-bit color, you could say, right? So the tile values are either 0, 1, 2, or 3. And that could seem like a very limited amount to work with, but the way we're going to make that a little bit more robust, or give the artist a little bit more room to work, is we're going to use palettes, right? We're going to use palletized color and have colors 0, 1, 2, and 3. And then because we're using palletized color, different layers can be assigned different colors, and then what we'll do is we'll have some type of presets for different color palettes to use. So when we look at how we're subdividing all of this data, you'll notice that each tile size has 3 layers. So for the smallest tile size, it gets the largest allocation, because the smallest tiles, you need more of them to fill the entire screen, right? And so you have 3 layers of each tile size. So for tile size 0, for being the tile exponent 0, you have these 3 layers, right? So tile layer 0, 1, 2, and 3, and then the next tile size up, it's twice as big, so you need half as many of them, so that's why this data allocation is smaller. You have 3 of these layers, and you keep on going down. Now the thing is if you keep on dividing the data like this, eventually you get one single pixel down here. That one single pixel is completely useless for creating 3 layers, because you need at least 3 pixels for 3 layers. So the smallest area down here is a 1 by 1 pixel, and a 1 by 1 pixel, and a 1 by 1 pixel, and a 1 by 1 pixel. And since it's not enough to encode 3 layers of pixels, what we're going to use that final pixel for is for encoding a uint32 value that stores what I'm calling a configuration pixel. It's actually going to store the palette, right? So since we're only using 2-bit color and we want to use some type of preset palette, the preset palette is going to be encoded by an integer pixel value in these bottom right-hand corners of each of these tiles. Okay, so now that we know what this interface is for kind of drawing, right? So we have this put command, we have this get command. We're really just only going to use the put command. The first thing we might want to do for this is erase all of the memory. And the cool thing is that since everything is just a big chunk of memory, we don't really have to do much. So I'm going to take the memory block that we're going to be using, and I'm going to define it over here. So define CPU pixels. And this is what we're currently drawing to. This is the 512 by 512 texture that we need to render, and it's also the 512 by 512 texture that we're going to output to a PNG file so we can visually inspect it. So we're going to undef CPU pix right here. So we're going to define it here, undef it there, and start drawing. Or, well, first we're going to clear it off, right? So for int... Or let's kind of keep to our defines. So int32 CLR for clear equals 0, and then CLR is less than or equal to 512 times 512 times 4, and then a -1. And we don't really have much room for that, so we're going to put this in a define. So we're going to define something like... max com, so max component index. Alright, so this is max component index right here, and then down here we're gonna undef max com over here, and then less than or equal to max com, right? So right, because here's all of the pixels. 512 by 512 times 4, because there's RGBA, and then -1 because the first component index is 0. Okay, so then CLR++, and then within this loop, it's dead simple. We just take this CPU pixel value, and we just say CPU pix CLR is going to equal a U08 cast of 0x000000. So we don't really have to obviously write out all these zeros, right? This is exactly the same as this, but I just want to make it a little bit more obvious that we have a RGBA, and I already screwed it up because RGB and A is all 4 bytes. This is only 1 byte, so that's what we want. So the way I write it in a way where, you know, there's more context clues, right? So it's much more verbose, but it gives me some context clues where I know that this is supposed to be a byte, and I can see from here it's supposed to be a byte. So just a lot of things to help you read the code without having to use any IntelliSense. So let's define U08, and then we also need to define int32. And we'll kind of like move this over here like this, just so that when we want to cut and paste to undefine this, right? Like if we want to really quickly write all our undefines, we can kind of do this nonsense over here. And now that I think about it, I'd actually like this justified like that. So I'm going to go over here for a second and do that. And then, right, we can make a little checksum over here to keep track of how many undefs we have, because we're getting a lot of defines for this section now, and we just want to make sure that whatever we define in this section, we want to undefine. Okay, and then same thing here, since we don't have anything that's too long right now, we have enough room where we can kind of shove this in here. Okay, and yeah, so let's just make a note of what we're doing here. So before we draw, clear our canvas. Right, so canvas is obviously a weird way to call it because it's a texture and it's a bitmap. Well, actually, this data here is just a bitmap, right? Because the texture is the same data uploaded to the GPU. But let's make a note of where we are. So @vid IID, and it is 94, and the time is right. So make a note of where we are, and then let's start drawing this pattern. So in order to draw the pattern, we're going to go from an Auset index that is... We're going to go through all the Auset... And we're not going to go through all the Auset indexes, or are we? Actually, we probably should. So for int32 os equals 0, and then os is less than or equal to, we could say 16 minus 1, so we understand that there's 16 of them. And then os plus plus. Okay. So we'll loop through every single offset, and within every single offset, we're going to loop through the edges of the tile set. So in order to do that, we have to think about how we're going to do that. What is an elegant way to loop through every single edge? We could just make 3 different loops in here. That would be, so let's not think about elegance, let's think about readability. So, and let's actually make some variable declarations here, just because I like things being kind of terse. So int32, y0, or x0, and, right, so x's and y's, zeros and ones. So this will be the location, and we might as well kind of like start CLR for clear, and then int32 os, right? So os for osdex, and what else? So right here, right? So usually we use these as bounds, so I don't know if I like this. Well, we use it for bounds, but we also use it for loops. So, yeah. So, bounds of what is currently being iterate through x and y coordinates by specifying the bounds of our double loop. So yeah, okay, actually that actually makes sense. So int32 tx. So this is going to be, if we look at our notes here, our notes file, right? So there's a local tx, local ty. So I believe with sometimes I use lx instead of tx. T is a little bit easier to distinguish than an L if you don't have a proper programming font. So maybe we'll just stick with tx, and this will be loc tx coordinate, and int32 ty will be the local ty coordinate, tx and ty, and we'll just do like a loop through the x's and y's. We want to do a loop over the y's first if we want like a proper scanline order. So let's just do, but you know what, the other thing is we don't really care what order it's drawing in. And if we don't care what order it's drawing in, we should do x's and then y's just for consistency. And I don't really care about the order of the drawing, so let's do something that's just more consistent and say that, you know, tx equals x0, and then tx is less than or equal to the x1. So we're going to loop through those bounds, and then tx plus plus. And then we're going to duplicate this and do ty. Or not, if we don't know what we're doing here. And yeah, so inside this double loop is where we're going to set stuff, and we want to do this kind of 4 times. So the first setup we're going to do is the top edge. So x0 equals 0, and x1 equals 512 minus 1. Right? And the idea here is that, we're going to hard code it, and if we ever want to, and we've done this before, if we ever want to swap this out for some type of configuration variable where we're using something that isn't 512 by 512, we can grab onto it. Whereas if we wrote this as 511, it would be a lot harder to refactor. And there is that term Yagni, you aren't going to need it, where you shouldn't do things like this, but I think it's okay to violate the Yagni principle as long as it's just simple, stupid things that don't take up too much of your time, right? It doesn't take up too much of my time to write it this way, but it's going to save me a heck of a lot of time when I if I ever need to refactor this. Also, I'm trying to keep this abide by the Twitch rules of keeping things kind of family friendly, so my channel doesn't have to be mature. However, I'm not going to, as long as it's not political, you can say whatever you want, use any words you want, I won't be offended. That's kind of like the way I'd like to play it on my channel. So, no, what do you call it? No offense given, no offense taken, right? So if I think someone's, trying to be purposely offensive, I'll straight up ask. Otherwise, I'm going to assume, what do you call it? Goodwill. So, just in case, because, I don't know, I don't like that I'm not quite myself on this channel, because, I'm kind of not talking exactly how I would normally talk, and that kind of bothers me because I think it's kind of ungenuine. So I just want to say, for the record, talk however you want to talk. The only reason I may be censoring myself is just so that I am, abiding by the Twitch rules. So, okay, so what we're going to do is, right, we're not actually going to iterate through the y, right? And then this is kind of redundant, writing the loop this way, but it's just the most dead simple way to write this, right? So, draw top side pixels / tiles of the active Auset. Right, so we can make a little note of what we're doing here. I don't think it would be helpful to say, what these are. And we also already have a commentary up here of what these are. So yeah, we don't need that. We can just keep this nice little block comment here to know what we're currently doing. And now I'm kind of annoyed because this is a little... Let's indent that. There we go. And we're going to do a whole bunch of these. But let's get the first one working, and then the next things are just going to be a lot of cut and paste code. So let's take this, and we don't want the get command, my bad. We want the put command, so let's just paste this in here. And let's delete all this commentary. Or do we want to delete this commentary? Yeah, I'm going to delete this commentary. And all these parameters need to be set, so... Actually, you know what? I could just keep it like that, right? We could just put this as a commentary over here on this side. So we got to figure out the tile quadrant. So it looks like we have to loop through the tile quadrant as well. And when we loop through the tile quadrant, we can just do the same exact graphic for each tile quadrant for now. And then if we want to get fancier, we can do, we can kind of specify... do something different depending on what quadrant we're on. Maybe we'll do like a base pattern that goes on all of the 4 tiles of the Auset, and then do something fancier depending on what quadrant we're in. But for now, we're going to loop through every single offset, but we're also going to loop through every single tile quadrant. So this is TQ for Tilqua for tile quadrant, and there's only 4 quadrants, so less than or equal to 4 minus 1, and TQ plus plus. Okay. And then we'll have to declare that variable up here. So int32 TQ is going to be TQ is for Tilqua, right? Tilqua for tile quadrant. So it's weird that I'm going to explain my variable names with like less abbreviated but still abbreviated names. But that's how I'm going to roll, which could make my code kind of hard to understand unless you've been familiar with it, but that kind of sucks, but I just feel like when you're juggling a whole bunch of variables, making those variables all like really long just makes it really hard to juggle all of this stuff. So that's kind of the way I write code. So yeah, we're gonna go through every single offset, every single tile quad, and we can, over here, we're gonna do UO8 cast of the offset, and everything. Now this local TX, local TY, I don't think that should be, actually no, the local TX, local TY can be 8 bits, because if we look at our diagram, so let's look at the diagram for a second for PAINT5D, we see that this section here is 128 by 128, and that means if we are, that the highest coordinate for local TX, local TY will be 127 by 127, right? And even if we smashed both of these graphics together, we'd be within a 256 by 256 region. That would make the max 255, and we'd still be able to use UO8. So just making sure of that, because if we get this kind of stuff wrong, it really burns us pretty bad. So this is wrong. This is the tile quadrant, even says over here. So so we can make a note of this, right? So we can make our little convention for saying, you know, this, aka this. And then over here, offset dex, we want to take the current offset dex and downcast it as well, so it has the correct bit width. And we can also say that, you know, it's os dex slash os. And the tile exponent. So we want to do this for every single exponent. Now the problem here is that depending on what exponent, the actual maximum here is going to change, right? So so let's draw every single tile exponent and draw like a rectangle surrounding the area. So in order to do that, we're going to have to unhard code this and figure out, well, what does the maximum coordinate need to be, right? So let's do for int32 te for tile exponent equals 0, and the tile exponent is, oh, this is not right. The tile exponent is going to be less than or equal to, it's going to be less than or equal to 7, but so we really don't want like magic numbers kind of lying around in our code. I do like that it is, well, I do like that magic numbers like this, right, and this, right, that they're there, but sometimes we want to have a way to, right, when you code magic numbers, it makes things less abstract, but then sometimes there's a trade-off between a high-level understanding and low-level understanding, right? We got more low-level understanding if we use these actual numbers rather than constants. To bridge that gap, to get the best of both worlds, what I like to do is just say, you know, assert that, and then go over to our data, and we already have constants for what these maximums are. So down here, we should have, where are you? You're somewhere in here. I know you're in here. PAINT5D data, right? And yeah, so this thing here, we can assert that for the quadrant here, we can assert that 3 equals the maximum tile quadrant, right? So this is for TQ, right? And then for we can do one for every one of these, right? So for the Auset, right, the Auset, the tile quadrant, and then the tile exponent, right? And then we can say, oh, the tile exponent, well, that needs to be up to 7, right? So we have the 7 here, and then we also have it here. The tile quadrant, that needs to be 3, but we have it written as 4 minus 1, so we should probably write it in the same exact way, just so that it's easy to see where that's coming from in the code, right? So write that as a 4 minus 1, write this as a 7, and then this thing that we're writing as a 3, that's not how we write it in the code, it's, oh, hold on, this is Auset dex, this is our 16 minus 1, my bad. So this is going to be 16 minus 1, and yeah, so we'll just write it like that. So we got 16 minus 1 for the Auset dex, we got 4 minus 1, and we got 7. Also, let's do this. We're going to do it exactly the same way. So now if we highlight these, we can see them used exactly where they're being used, right? So bam, right there. Okay, cool. So now that we have these asserts to kind of give us some understanding of what the heck we're doing here, we need to, well, first of all, we got to make sure this a triply nested loop, and it is. We need to figure out the maximum for the x and y, the maximum coordinates. So we have some type of function to convert to maximum coordinates. Let's look for all of our stamps here, all of our breakpoints, and let's kind of remove the old breakpoints. Just give them a quick glance in case anything kind of like stands out and looks like it needs attention. Right, so I like to do this individually rather than nuke them all at once, just in case there's something I forgot about, because sometimes there might be a breakpoint on a to-do message. It might be very important, so I like to just go through it like that. Okay, so there is a function that converts to maximum coordinates, and hopefully in my PAINT5D notes I can actually find that signature. So got Glock picks to pane picks to Glock picks. These are coordinate conversions. Bit packing, bitpack put, bitpack get. So we have some camera controls. So it looks like it's not in here. So we're going to find it. So it's called max core, MAXCOR for maximum coordinate. And we can see it's called tile exponent to max coordinate. So we're going to go all the way up here and find it. So yeah, PAINT5D tile exponent to maximum coordinate. So the first thing I want to do is say, is it in my notes file? And if it's not in my notes file, where are we going to put it? So we got this main interface. We have coordinate conversions, and is this a coordinate conversion? Tile exponent to maximum coordinate. I would say that it counts as a coordinate conversion. Yeah, I would say it does count as a coordinate conversion. Oh, got you. So we're not doing this. We're not doing this because I don't want to wrap things in extra structs, because it just makes the code harder to follow. It makes the code less clunky when you do that object-oriented style of, you know, roll things up into objects and pass those objects. Like if you're going to pass a whole bunch of parameters together all of the time, right, like how we're doing here and here, that is a code smell of implied object. But just because it's a code smell doesn't mean it's necessarily a bad thing. We do it this way so that we can really kind of get a feel for what the code actually is doing, rather than hide it in structs. So this is a coordinate conversion function. So we're going to put it down here. And so UO8, and then here's the function name, and then it's going to take a UO8 of tile exponent. And let's kind of like align that nicely so we see that, you know, this is the input here. And there, so now we got like a little signature for this function that we need to use. So it's in our like documentation or in our notes file, right? So the idea is so that I can reference my notes file here to know what I need to paste into here, which is kind of hacky, right? Because it's like, this is not code, this is just a notes file. And you might say, why not use a header file? And the reason I don't use a header file is I don't want for declarations in my code. Now, we could use a header file and include the header file after the implementation, and that would solve it. That's kind of hacky. That would solve it, but I would rather just avoid accidentally forward declaring any kind of code. So we're going to do that by not making any header files and just pasting into notes file, which the danger of that is that the notes might not actually reflect the actual code. But remember, we're coding for rigidity, not flexibility. So a lot of times when we write notes, those notes aren't really going to be subject to very much change, right? Sometimes it will change, but most of the time this stuff is not going to ever change. So we're going to take this function here, and we're going to call it up here, right? So tile exponent to maximum coordinate. It's going to take TE, and we just want to say MC. So MC for max coordinate. And then we can go over here and say, and figure out, like, where are we going to put this? And I don't know where this should go. So we have Auset TQTE. We want to kind of declare them in the order that they appear. Okay, so the tile exponent, and for tx and ty, we really use the maximum coordinate first. So let's do MC. Maximum tx or ty. Right, so this is the maximum tx or ty coordinate right here, MC. And MC is a U08 value, so we probably shouldn't do it. Well, we could still keep it like this. Like, if we want to just, the idea here is that we're not really worried about efficiency here. And since we're not worried about efficiency, we don't want to shoot ourselves in the foot with any, like, typecasting problems or, like, integer overflow problems. And so we're going to use a bigger bit width than we actually need, just so that we can avoid some problems, right? So we're going to do, like, a U08 cast of, or a int32 cast of this, right? So this returns a U08, but we're going to do an int32 cast. So, right, and, right, so maximum coordinate. We can also make a note that we could go over here, we could do something like this. What we're actually doing, aka tile exponent to the max coordinate, right? That is what's going on here. And tile exponent, maximum coordinate. And once we have this maximum coordinate, rather than this 512 minus 1 that we're using for the maximum coordinate here, we're just going to use MC, right? MC is going to be put right here, right? Now, the maximum coordinate really doesn't change for... Okay, yeah, that's fine. So let's indent this properly and see what else we have to do. So this tile exponent, local tx and local ty. We should already have that, right? So it's a, we do a U08 cast of tx and ty. And we're going to keep up the convention of saying that, you know, loc tx slash tx or ty. Okay, so we got tx, we got ty, we got the offset, we got the tile quadrant that we're drawing in. So the tile exponent, where are we getting this? So te, yeah, so we already have te, okay. So tile exponent, we're going to do a U08 te for tile exponent, and indent that. So te. And I know that this looks like division, which could be kind of confusing. But the thing is, I could either use this or I could use an OR symbol. And an OR symbol, well, technically that would be bitwise, and that would still be confusing. If we could interpret this notation as math, we're always going to be confused. So we want to use something that makes more sense in common English. So when you're writing something in English on like Facebook or something, like a slash, this slash that is going to be more understandable in the common way people do things than a bar symbol. So that's why I have a forward slash instead of a bar here for or. But these slashes mean or, but they mean or in the sense of like English, or if that makes sense. So this tile layer here, do we have the tile layer? We need to go through all the different layers, and for now, we're just going to draw on every single layer the same exact graphic. So we're just going to add that here, right? So for int32 tile layer equals 0, and the tile layer is less than or equal to, and the tile layer should be less than or equal to 3 minus 1, because there are 3 layers, and tile layer plus plus. Okay, so now we're kind of triply nested, or quadruply nested in here. And then up here, we have to make one more assert, and this is going to be 3 minus 1, and it's going to be the maximum tile layer, and I already know that it's till lay like that, so I don't even need to look it up. TL for tile layer, max tile layer, and if we highlight this, we can see exactly where it's used in the code, right? Okay, so tile layer, let's declare that here. So int32 tile layer, TL for till lay, tile layer. Okay. So now that we've done that, what else do we have to do? So we're kind of filling all this in. So it looks like we almost have everything filled in here. So U08 TL for tile layer. And I think what we're going to do is we're going to use a different color depending on what tile layer we're on, right? So we have 3 layers, and we also have 3 non-zero tile values. So we could make use of that, right? So so for that, what I'm going to do is just say that for this tile layer is specified here. So we're going to do tile value equals TL, and we're going to assert here that the tile value is less than or equal to 0, 1, 2, 3, is less than or equal to 3, which it should be, but we're going to do the tile layer starts at 0. We don't want to use the 0 tile value, so we're going to add 1, right? And we could also do another assert for that. So for tile value, we have 0, 1, 2, and 3, so there's 4 tile values. However, this is binary, and because it's binary, we're going to do B11, and this is going to be for the tile value. So tile value, we're going to make it B11, and then over here, we're going to just make a note of that. So define B11 is going to be 3, and it's, make a note, binary, right? So that's what we mean by B11. And just make a note of that, and then let's kind of do this just for nicety here. Okay, so now down here we're going to have to do B11, make this 05, and What's next here? So yeah, we can make a note of what we're doing here. Use a different... Have the tile value depend on what layer we are on, as this will be helpful for debugging the pattern when we are inspecting it in MS Paint or rendering it with GLSL code, right? So that's why we're going to do this. This is why we're going to link it up like this. And we need to make a note of kind of like where this is. So this is at vid.iid. The video is 94. At the time is 57 minutes. Okay, cool. So, a little note of how we're calculating this tile value. Now, tile value is not declared yet, so we got this tile layer, and we're going to do int32 tile value, TV for tile val. Okay, so now we have that. We need to make sure that when we set the value, that, oh, here's tile value. I'm like, where are you? Okay, so tile value, let's put that here. So it's going to set it to UO8. And tile value, aka TV. And the thing is you know, we're not always going to get so lucky to where we can abbreviate to exactly 2 unique letters. Now, when we can, we'll take advantage of that to be able to make things nice and terse like this. But it won't always be the case. Sometimes we will intentionally make variables that can be abbreviated to 2 letters. So we'll make, like, the variable might sound a little bit weird, and we did it just so that we could make it unique, right? So if I ever need something, so this is tx, ty for, like, tile y, tile x, or whatever. You know, if I wanted something called texel x, texel y, well, we already have tx, ty, and so maybe instead of calling something a texel, I would call it, like, bitmap x, bitmap y, or something stupid. There is definitely the potential for me to do something like that. So, we have the quadrant, the exponent, the layer, the x and y, the offset dex, and the tile value. And so this is kind of in a general specific manner, though you notice that the tile value is kind of separated from its friends over here. The reason for that is it is the value that we are getting or setting, right? So for this put command and this get command, it is an output parameter or an input parameter, right? So it's an output parameter here, and then it's an input parameter over here. And I want to just... for the ease of use, especially cutting and pasting things or remembering the order of the parameters, I thought to make the get and the put have all of the parameters in exactly the same order, so there's less to remember. That just seems like a good idea, and so far it's helped me out a lot. So right, you keep all these parameters in the exact same order. The only thing that changes is the tile value. When it's a getter, this is a pointer, right? So yeah, so that is why this tile value here is kind of separated from its friends. It's because the tile value is an output parameter, and output parameters are usually the last parameter when you're writing idiomatic C code, idiomatic C code. I don't know how you call it, but anyways. So yeah, we got this put command, and you'll notice that the put command is actually hard-coded for this CPU pixel. Like, we don't even have to define this here because, oh, well, we do because we have to erase it. So we could make a note of that, right? So, right, this is hard hard-coded to use CPU picks. Alright, so we could just say CPU picks here, right? So CPU picks is this thing. And yeah, so we have this loop, and the next thing is, well, we want to loop through every single edge, and this is the top edge. So to get all the other edges, we need to just redundantly do this over and over and over again. And the thing about that is the code is kind of what do you call it? There's a lot of excess code here where we're gonna like loop through here, and do you really want to copy paste this thing 4 different times for the 4 different edges? Or do we want to be a little fancy about it? And I think we could be fancy about it, so we could say that, let's do this. So over here, so what we could do so we're starting 1, 2, 3, 4, 5. So there's 5, 1, 2, 3, 4, 5. We're starting to lose track here. So we could do EE for edge index, right? And then okay, EE for edge index. And then down here, what we could do is we could say, you know, if right, we could say top left. And we could copy paste this. Else error a bad edge index right, make a little error message there. But yeah, we could have an edge index variable that will set what we're going to iterate over, and then we only need this one loop here rather than copying and pasting this multiple times. That'll save us a little bit of space without being too abstract, I think. So you know, go through the x bounds, go through the y bounds, and set whatever you need to set. So draw one of the edges. Right, so we're gonna draw one of the edges. Right, so draw one edge. We have enough room to where we could make a label for this. Let's make this lowercase. Draw one edge. And draw one of the edges. Let's remove this. Okay, so we're going to draw this edge, and this will be configure edge to draw. So we're going to configure the edge to draw. That's basically what we're doing here. So we're going to configure the edge to draw, and then we're going to draw one edge, right? So okay. So now we just need to go in order. So we're going to go top left to top right to bottom left to bottom right. And that means 0, 1, 2, and 3, right? In a traditional scanline kind of order. And for the top left, right, that is we're moving along on the X, and the Y is kind of like maxed out. So it's going to be 0 and 0 here. So rather than... I don't know if this commentary is... I don't know if this commentary is necessary for all of this. So we could say, you know, we just want a single line of tiles drawn around the borders of the currently active subtile of the active Auset. Right, so this is what we're kind of doing here. We gotta still configure this, but let's just make a note. This is 94, video 94, and the time is 1 hour, 7 minutes, and let's say 5 seconds. And the reason I'm going to write it like this is just because I don't think I want to clutter up the little statement I made down here. So these are all the different edges, and they're the different locations. So for the top, so these are really corner locations. This doesn't really make sense. Yeah, this doesn't really make sense, does it? I was thinking in terms of corners, but that doesn't really make sense unless we're talking about going from a certain corner and then drawing. Yeah, that still doesn't make sense. I mean, we could do that, but no, this is kind of confusing. So we're gonna do the top edge, and then we're gonna do the I think the top edge, the bottom edge, the left edge, and the right edge, right? So here's what we need to do for the top edge. We need to just move along the X, but the Y stays at 0. If we're going to do the bottom edge, it's going to be the exact same thing, except this is going to be maxed out at the max coordinate value, isn't it? Yeah, so I think I want to separate these values just so we don't get too confused when we're looking at them. I really want to kind of visually group those together. Hey, so I see somebody kind of stop by in here. So I see 2 viewers. I'm just going to throw my demos in here really quick. So if you've never been to my channel before, here's some technical demos. I'm working on an engine that is going to create fractal auto-tiling. If you don't know what auto-tiling is, that makes it kind of hard to explain what's going on. But if you check out those demos, you'll kind of see the kind of tech that I am going for here. Okay, so the bottom edge, right, we're just going to go on the bottom. So static. So the static is the bottom here. And then over here on the top, the static is the top, right? The thing that doesn't move here. Right? So I'm just making notes as I write this to make sure I don't do anything stupid, because I'm pretty good at doing stupid things. So left, for the left, we want to make sure that we go from 0 to MC, right? We want to move along that left vertical edge. And for the left edge, everything's 0, right? So this is our static for the left. And this is the part that moves, right? This part moves, right? To draw that edge, we got to move on the Y. Now, for this last edge, the right edge, it's going to be the same kind of code here. So let's kind of cut and paste this really quick, and then make a note that the static part is going to be the, or actually no, static is still this, but it is the right, and then we're going to change this from 0 to MC, right? Okay, cool. So now when we're looking at this, we want a way to kind of confirm that that our code is correct. So one thing we can do first is we can see that static, there's 2 instances where our static comment is at the bottom, and there's 2 instances here where static is at the top. So everything is balanced, right? And if we can make sure that everything is completely balanced, then we have some assurance just visually that everything is correct. For instance, I see here's one thing with 3 MCs. This also has 3 MCs. Then I have something with 1 MC and 1 MC, right? So we also have a balance there as well. So it looks pretty balanced to me. We want to do like one more mental check to make sure that we know what we're doing here. So we're saying this is the top edge, so we're going to move on the X. So we are moving on the X. Move. So we could say move on. We could say move on X-axis, and then for the bottom edge, we're going to move on the X-axis as well. But we're going to be at the bottom for the Y. So right. So we could make a note of that, where move on Y-axis, or sorry, X-axis again. And then down here, the left edge, for the left edge, we want to move vertically, so that's why we're moving on the y-axis, and we're all the way over to the left. I get my left and right mixed up all the time, so I just want to make sure that's correct, and that is correct. So let's make a note here that this is move on y-axis, and I didn't spell move on correctly here, did I? Move on, move one, move on, there we go. Move on, x-axis, move on, y-axis, and then we'll call this one move on y-axis as well. Let's double check that though. So now x is all the way over to the right because we're doing the right edge, and we're going to go from 0 to MC, right? So we're going to draw along that edge, right? We're going to move on the y. So that all looks good to me. So now we can kind of double click this and say, okay, so we have 4 different move-ons, right? Because there's always going to be one axis that we're moving on when we're drawing an edge, and there's 4 of them because there's 4 edges. There are 2 x edges and there's 2 y edges, so we see x-axis and y-axis, so that makes sense. So we have just little ways that we can kind of check really quick that everything is balanced and everything is analogous and everything looks good. So everything looks good. Let's just clean up our formatting, make it very consistent between all the different blocks, so that looks good. And we are we ready to finish this up? I think we're pretty much done with this function right now. So this is for draw default offset. And if we go down here, we got our put command. The next thing we want to do for a sanity check, right, is we want to take all these values and kind of highlight them really quick and be like, hey, are you represented in here, right? Like, do we have right, so look through here and color all of this, and then go up here and say all these are colored, the offset, right? So this is the edge index, so that's fine. TX and TY is colored. MC is not colored because it's over here, right? And just do like a quick sanity check where we're kind of just using our token highlighting to just do a quick sanity check to make sure that everything has been represented, right? So if we do the offset, the tile quadrant, the tile exponent, the tile layer, the tile value, and the tile x and the tile y, those function signatures, every single parameter should now be colored. So we're just going to double check that right there. We can see, oh, yep, every single parameter has been colored. And then we see we're looping through tx and ty. That's excellent. One more thing we might want to do is check the x's and y's. So anything that's x will color this color. Anything that is y is this color. And then we'll just look for any kind of transposition mistake. So we have the correct color groupings here, and correct color groupings here. So no transposition mistakes. And you'll say, yeah, this is kind of redundant and stupid and it takes up time. But the thing is first of all, we're not going to write any test code for this specific thing because we just want to visually confirm it. And even if we were going to write test code, writing test code just will say that the test doesn't work if we screw this up. So we would like, and then we have to actually find where we screwed up. So making a lot of effort to write it correctly the first time could save us a lot of headaches. So transposition errors especially can be a big headache to debug or find them once things are going wrong. Yeah, so I mean, this looks good. I think that everything in here is correct to the best of my knowledge. And we are ready to ship it. Now we have a little bit of room here, so I mean we could make a little checksum here if we wanted to, right? We could make a note here of what these numbers are. So I'm gonna do that. I have enough room. Do I have enough room? I have like almost enough room. The parameters don't have to be double digit though, right? Because we only have like 7 parameters, I think. Insert key 4, 5, 6, and 7. I just like checksums. So yeah, we got 7 parameters here. Looks good to me. Yeah, so this looks good to me. I think this is properly written. There's 5 defines there. There's 5 defines here. Yeah, that all looks good. So we're gonna just try to compile and make sure that this works. And then we will have done, if we look at our agenda screen, actually, yeah, the default fill pattern, right? So this is the code for the default fill pattern, but to get that default tile, we need to like press like P for pattern to like make that happen. So we still have to figure out the keyboard bindings, but we have the initial function we need. Hold on, let's go give this a run and see what happens. And we got a little bit carried away with our commentary, and it looks like we probably inlined a comment within a comment. Yeah, comment within a comment. So let's go over here and look at where we're writing a whole bunch of comments and be like, I don't see it over here. 3172. Yeah, right here. Oh, I see. Oh, I see. Okay, yeah. So we could just fix that. Like that. That looks kind of ugly. I'm going to write it like this. Okay. So got rid of that comment within a comment. We're going to give it a run. And error. So we don't have an error macro yet. So let's define that. Define ERR. It's going to be AAC 2020 PAINT5D halt. And that is our 6th macro. And then we'll go down to the end of this section and undefine that. So right here, we're going to undef ERR for error. 6 of them. Okay, cool. So EEE for edge index, unused variable. So how did we make this an unused variable? Because I thought we looped through this, did we not? Oh, you know what we did? All of this is bad. Right? All of this is all, right here, this is all variable shadowing, right? Because we decided that we were going to put all these variables, we're going to declare all of these variables outside, right? Right, all these variables are declared outside, and then we're all, like, redeclaring this here. And it says unused variable EE, right? And that is likely because of the variable shadowing we're doing here. So let's not shadow our variables like that. Variable shadowing is bad. So let's make a note here that at vid IID 0094, and the time is 1 hour, 19 minutes, and 40 seconds. And we'll just say that, you know, variable shadowing is bad. Rewind the video a minute or so to see what I just deleted. Right, so make a little note of this, right? We do not want to shadow variables. Okay, cool. So we got rid of the variable shadowing. Let's give it another run here. And I'm hoping that CLR, unused variable CLR. So why is that? Didn't we use CLR over here? Oh, once again, variable shadowing, right? So delete that. We were shadowing this variable because we decided to declare it up here, which is kind of wasteful in terms of memory, because the entire stack frame for this function scope is going to have all of this stuff, when not all of these variables are always used everywhere, right? So we really only need this variable for the stack frame for this loop here. But you know what? We're not worrying too much about efficiency for this function. We're really mostly worrying about how readable it is, right? Because we're not going to be like executing this like frame by frame. This is going to be a thing where we press a key and a thing happens, and then we're done, right? So we don't have to worry about efficiency. We just got to worry about readability. So I got to turn off my hotkeys here. Suspend hotkeys. Okay, cool. So everything is still working. You'll notice that the PAINT5D shader, shader number 1, is now just a magenta screen, because it's under construction now, and we kind of nuked the old code, and we're writing some new code, right? Because the old code kind of just verified that we actually were getting access to the texture memory. And now that we know we have access to the texture memory, we got rid of that, and we're going to actually write the proper shader code that goes here. But before we do that, we want to make sure that the data has the structure that we think it has. And so we're going to use this default draw command to make that happen. So let's go over to our notes file and say coordinate conversions. Technically, this is going to be bound to the keyboard. Right, all these commands here. So yeah, we're just going to add this to bound to keyboard, right? So it is also void, so let's keep the same pattern going here. So it's a void function. Is my caps lock on? It is. Where is caps lock? I never use caps lock. I always accidentally hit it, so I never know where it is. There we go. Okay, so we're going to say void, and then this is the command, and it also takes void, right? It also takes void. Okay, so draw default Auset, and we're going to make that... we're going to tie that to the P key for a P for pattern. And so to do that, we're going to have to open up our keyboard bindings. So we have a file called keybind. And if we look at the data, yeah, so P5D, camera control, move brush, etc. We got all these nice little commands here. And we're going to make another one. I think we'll call it CHRP5D. Do you just want to call it default pattern? A default pattern is something we're not going to use as much as some of these more tourist things, so I think just calling it do we want to call it default pattern, or do we want to call it default Auset, right? Now, we don't have many keys to bind to, so even though this is called 1, I think we should just have one key for the default Auset. default offset, or we could call it default pattern. I don't know. Well, we could do this, just call it DDA, right? Draw default offset. I could do pat DDA for pattern draw default offset. Right, because we want to do P for pattern, right? Because it's on the right hand side of my keyboard. So I might want something where I can remember what's going on. Or we could just call it pat, right? So the longer we make this variable, the harder it's going to be to remember what it is called. So I don't know. Why don't we just call it pat, right? So pattern. We could say pattern draw default offset, right? Have a little note of what that's going to do. And this is where it's declared. And then we also want to do over here, right? So this is PAINT5D, and then somewhere we're kind of assigning these, right? So in the side, the PAINT5D initializer, we have everything we're doing here. So let's kind of say, it looks like we're kind of sectioning these off with like a video integer ID of like where we are in the code. So let's kind of keep with that pattern and just say, where we are right now currently. So at vid IID 0094. It's also interesting to see the last time I was in here. So 12740. And I'm going to say draw default offset pattern. Pat equals pattern. Pattern using the P key. Be careful. This will nuke your... Right, this will nuke your work. To do, press it 3 times in a row to make it work. Make a key combos so we'll make like a key combos sublibrary at some point where we can have different key combinations to invoke behavior, but for now we don't have that. We want to keep our keyboard handler as simple as possible, so for now we're not going to have any type of keyboard combination things. But let me make a note of this one more time. So okay, done explaining. Okay, so we're going to, or actually no, we'll write some more stuff here first. So comma dot P5D pat for pattern equals single quotes capital P for pattern, right? So and then we can make a note of what we're going to call, right? So P for pattern, and calls the function okay, so we have the function that we're actually going to call, and then we have this here. Okay, so we're at 30. And yeah, so we'll wait for a second. Okay, so we're done explaining this. P5D pat will be the symbolic name for setting a pattern key, right? So this is the command for this, right? We're adding a little bit of indirection, so we're not wired specifically to the P key, but for right now, P is for pattern, and this is PAINT5D pattern, right? And it's going to execute the function on my right here to draw a default auto tile set pattern on all of the different layers of the texture memory, right? So we're going to loop through, it's not just on one thing, it's the whole thing. We're going to loop through all the different Aussets, all the different tile quadrants, all the exponents, everything. We're going to draw on everything and create this just very basic default tile set just so that we can inspect it in MS Paint, right? Save it to PNG file and kind of see what it looks like. So now that we have this keyboard binding, we actually have to implement it somewhere. But before we do that, we want to just make sure that we haven't done anything stupid and that this still runs. So yeah, so this still looks good to me. Okay, excellent. So what's next here? I mean, well, we got to figure out where the keyboard listening kind of stuff is going, right? And one way to figure that out is, well, we got this, right? And we know that we have, I don't know if we've implemented the camera controls yet, but we should have them. If we don't already have them, then we need to do that now. So let's look for where this is being used and see if we have implemented the functionality yet. So we're going to do a find all. So we have the bindings, but have we actually used them? So we have if char key equals this, so it looks like paint5d.f. Oh yeah, so paint5d, right? It's editor centric, so the actual editor is paint5d. And I don't want two of these files open at the same time, so let's close this and move this over here to this editor. That did not quite work as I wanted it. So we have some control F help, that's nice. So key in, right? So we're taking a signed char that represents a keyboard key, and then we're doing some stuff with it. So here's actually where we want to do that. So let's add that in here somewhere. So we got big if else, left, right, up, down, zoom camera, etc. Move brush, all this stuff, right? So we could put this, right? We put the default pattern like at the top of all this. So let's just say overwrite editor with default Auset pattern. Right, so in here is where we're going to do that overwrite, and we're just going to say that, you know, if the character key is equal to key P5D, so this is most likely a macro, and it's going to be P5D pat, and if that is the case, then we can look at our notes, right? We can actually reference our notes here. So in our notes, we're going to call this guy here, right? So that's all we're going to do. Just bam, call that, and that's all we need to do, right? So now that's bound into, it's bound into the editor. Now we might want to make a log for this, so we might want to say that, you know, log and alright, so the command is P5D pat. So for this log command, we're actually going to have to define what log is. So it should be define log, and it's going to be AAC 2020 PAINT5D info any should be our logging command that just takes anything. And we have 4 defines, so let's kind of make this a little bit nicer. So we have 4 defines now, so let's make a little checksum here. Okay, and let's go down to... Oh, that's kind of ugly. Can we kind of move this around a little bit? Just make it so that when we paste this, I want to be able to just... it to just kind of... boy, this is getting kind of ugly. So I just want this written in a way where I can easily cut and paste it into the bottom and undefine everything, right? So these are my defines, and now that I've organized them like this, what I can do is I can go all the way down to the bottom of the section, and I can just go, bam, paste that there. I can change this to undef, add a space, go over here, and just nuke all of that extra stuff out. We now have successfully undefined everything. Okay, cool. So now we're using this logging function right here. However, the logging function might not show me anything because of logging function can be turned off for different systems, and I may have turned it off. So we might just want to call this actually want to call this a printf. So printf. And the next parameter is void. I think that will work for printf. I don't know if that'll work, but we can give that a shot and see if that works properly. So let's give this a run, and we'll just press the P key and see if we can see it in the logs, right? That's all we got to do. But also, if we're going to do that, we're going to need a flush std out if we're going to do it this way. So, okay, cool. So let's give that a run and see if we can... if it's wired up to the correct key. So, implicit function declaration. Okay, so, this must, we put it all the way at the bottom, didn't we? And this is a function that is wired to the keyboard, functions wired to the keyboard, so we actually need to move this up. So we're going to take this here. We're going to take all this code, we got to just move it up. So let's take it, I'm going to copy it, or cut it, and then we're going to find where we're calling it from. And, this says functions wired into keyboard, but it's not just functions wired into keyboard, it's also tau uniform controller, whatever the heck. So what we're going to do is, we're just going to make another section, right? So there's obviously more things that can be wired into the keyboard than just this. So we're just going to paste this here. And then what we're going to do is, we're just going to relabel it as functions, right? So this is also functions wired into keyboard. So we might as well just kind of reuse this label, which is kind of confusing, but I think that kind of makes the most sense for how we've organized the code previously. So just like, there we go. So we got this default. To make it a little bit less obnoxious, we might want to make this one lowercase. And functions wired into keyboard, right? Yeah. Copy that. And functions wired into keyboard, and then this is right. So these are two section labels, but functions wired into keyboard is that section is duplicated twice because default fill pattern thingy, right? This thing is wired into the keyboard, so that's good enough for me. Let's give this a run, see if this will actually compile. So printf, cmd, whatever, too many arguments for format. So yeah, so it doesn't really like me doing it that way. I just thought that maybe that would work if we could just change it really quickly, but it doesn't, and that's not a problem. We just have to take away this extra argument here. Just say, nope, you're not expecting that. Write it like this. That's fine. Okay, so now, if this works, we don't really have much feedback, right? We'll just press the P key and we'll see a log message, and, right, and then we'll have to actually output to a, we're going to output it to a PNG file so we can get some confirmation that that is working. Now this is taking a little while to boot up because I turned off, quote-unquote off, the unit test for PAINT5D, but my off switch is a intentionally unreliable off switch, so when I turn a unit test off, it just means it infrequently randomly executes sometimes when you start up. And that's just because I don't want to have I didn't want to implement a master kill switch that would cause the code to completely rot, so that's kind of my solution here. Okay, cool. So we have this working. I'm going to put this on a different screen so I can see the console here. Or actually, you know, this is a Windows program. Why don't we just move it over here? Nice. And now let's press the P key. And we now see that P5D pat, and we're skipping sync. Now the thing that kind of is bothering me here is that pressing any key is causing PAINT5D to re-init. But when I do press the P key, we are getting the correct command to execute, but we're getting the whole system to call its reinitialization code. And that seems pretty dirty. Same thing if we press the 1 key. So we have some type of mistake we made. We need to fix that eventually. But let's just get things working first, and then we'll fix this ugliness that is reinitializing the system every time I press any key, because that is kind of stupid. So we need something for the O key for output, right? So we're going to keep things that we use infrequently, we're going to keep them to the right hand, right? So left hand on the keyboard, right hand on the mouse is how we want to use this editor. So things that we don't want to do all the time are going to be on the right hand, so that you have to take your hand off the mouse and move to the keyboard. So let's look at our bindings for the keyboard, and we're going to add one more binding, and it's going to be for the saving. So let's just call it, you know, CHR P5D. Well, if we do save, then you think of that as the S key. So instead of calling it save, we're going to call it out. O for output. Output slash save uses pick save. We could call it picks out, but that would just be more confusing, right? You would read the code and you'd be like, what the heck is picks out? So we're going to call it P5D out. And then down here, we're going to make a Control F help section down here, because I think that there is definitely the potential for me to forget what I named it, because I named it kind of weird. So if we find that we ever use, hold on. If we find that we ever used if we're searching for P5D save and we can't find it, we want to know, well, why not? Why can't we find it, right? And the reason is because it's not called P5D save, right? It is called P5D out for output, right? So that we can associate it with the O key, right? Which is kind of awkward, but that's the way I'm going to do it. So if we see P5D save, out for output rather than sav for save. So out is for output rather than sav for save, so that we can more easily associate with the O key on the right hand instead of the S key on the left hand, right? So, and the time is 1 hour, 46 minutes, and let's just do 47, right? So this is just a little Control F helper section, where if we search for P5D sav or P5D save, it's going to tell us that this is actually what we need to use, right? Because we've named it P5D out, which is something that I'm thinking we may not remember in the future. So we just want to make a note of that here, right? So that if we forget that we called it P5D out, we can search for P5D save, and it'll bring us right here, right? It'll bring us here, and we'll be good. Okay. The next thing is, if we check our title screen here, this was the default tile. So, part 26, and then we need a pick save O for output. So we're going to, I need to take a break anyways. So what we're going to do is, I'm going to stop this stream, and I'm going to start a new one under the O for output section, right? Because we've done the default tile kind of code. We haven't confirmed it yet because we need to save to a PNG file first, and that's kind of what we need to wire in next. But let's do that later. Let's do that in another stream. So we're going to look at our push-ups here, and it is still Saturday, right? Yeah, we kind of went to bed like early this morning and woke up at the same day, so it's still Saturday. So what we're going to do is we're going to make a note that we need to do 40 push-ups, and we're going to change this right now. So I'm going to write down on a piece of paper here that I need to do 40 push-ups. And I'm going to put it on top of my keyboard right before I end the stream. And we're going to edit some of these numbers. So we're going to add 40 to everything. So this makes this a 120. And this is the same thing, so 120. And are these still from the same day? I don't know. I haven't been very good at keeping track of these numbers here. I'm pretty sure 116. Is it the 16th? Whoa, okay, so those were streams from also today, huh? It's fair enough. Yeah, it says 116. It's still 116. So we're going to change this last thing and say that we're at, like, 1 hour, 50 minutes. Okay, and yeah, so we're gonna get out of here. So, so here's the title screen. So this is what we've done, and the next time we're gonna do the O for output key, maybe in 30 minutes to an hour. So I will be back later.